Hi, welcome back. Now, in the last video, we encountered a problem with our animation, which was that if we had too many people, too many individuals, too many points in our animation, everything started to be super slow. The animation just slowed down dramatically, and it was not really fun to look at this anymore. Now, before we'll go back to the coding and to fixing this issue, let's think about this once more. Now, let's say we had an example like this right here, where we have our screen, we have a bunch of white dots, that is people that are healthy, and we have the infected person right here. Now, the way that we have been doing this before is we were computing the distance between this red dot and every other point on the canvas. So essentially, in this scenario here, we would have been running 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different checks. We would have computed 18 distances, and then we would have compared whether or not these distances are within whatever distance we defined as the critical distance for an infection to occur. Now, here I've just drawn an arbitrary circle around the infected person, and let's say this is the distance within which infections can occur. Now, the problem is, of these 18 points that we're checking, there's really only these two that will wind up within that distance. Now, of course, the computer, the animation, does not know that beforehand. It only knows that after it has run all the checks. But wouldn't it be nice if we weren't searching, if we didn't have to search the entire canvas, but only a fraction of it, only the local area around that infected person? And we can actually do that if we use a grid structure. So what I've done here is I've drawn a grid onto our canvas. So I've divided our canvas into equally sized cells. So we have these tiles, these little squares. I mean, this could also be rectangles. It does not have to be squares. So let's just call it cells. So we have these cells all over the canvas, and I've set their size somewhat in proportion to how large this infectious distance is. And given such a grid, what we can do is the following. Instead of checking every point, we will now traverse every cell. So we'll start over here at the very top left, and then we'll ask, are there any infected people within that cell? So we'll have to store people within these cells. And if they are not, then we can just move on to the next, and then to the next, and the one after that, and so on, until eventually we'll reach this particular cell right here. Now, there is an infected person in there, and now we'll run a check on, not only people within this cell, because this would only include this person here, but we'll have a look at this entire area. So this cell and all the 8 neighboring cells around it. But we are not going to be checking every cell in the entire grid, in the entire canvas. So really only these 8 cells, and this is, it's just 4 people in the end. So instead of looking at 18 distances, we're now looking only at 4 distances, and this makes for a far simpler mathematical problem that the computer can solve in a lot less time. It's a lot more efficient doing it this way. At this point, you might think, well, isn't it kind of weird that you're first computing this grid and then passing the people, to the individual cells of the grid, and then you're traversing all the cells? And at first, yes, that seems a little bit weird because that incurs a lot of overhead. So it's kind of like a fixed cost that you have to incur at the beginning of each loop, like at each iteration of the loop. But trust me, it really pays off if there are like thousands of points on the canvas. If we do not have to run all of these tens of hundreds of thousands of checks all the time, we really save a lot of money. That makes that just makes up for having to compute that grid at the beginning of each iteration. And yeah, we'll now implement this. So we'll create a new class for the cells and then for the grid, and then we'll store the people within that grid, within those cells, and then we can locally search the grid instead of having to look at the entire canvas all the time. I am back in the editor now, and I'm going to go, I'll scroll down past the color definitions right before we define the person class, and here I will now define a new class called cell. Now, what's a cell going to have in terms of its properties? Okay, actually, I should use these empty parentheses here. I mean, these classes don't inherit anything, so I guess it doesn't really matter, but I'm just going to put them there anyway. So the cell, we'll define it with our initialization function, and we'll say that every cell will have a row and a column. Okay, so we'll say self.row is equal to row, and self.column is equal to column. And then lastly, a cell can include a bunch of people. It won't work like this. People is an empty list, and then we will fill that list. Now, what's a grid look like? A grid, create a new class. We'll initialize this grid, and we'll say that a grid, well, it sort of depends on the people that you pass into that. Okay, so people will be one of the parameters that goes into the grid, and then we have two parameters that determine the horizontal and vertical size of each cell within the grid. And we'll simply call these two parameters h size and v size. And I think we'll initialize them right away to two default values. I'm just going to make this a square, so 20 by 20 pixels. Okay, so let's declare this in terms of properties. H size is equal to h size, self.v size is equal to v size. Then we'll have the number of rows, and the number of rows in our grid is really just our height divided by the vertical size of each cell. And then we can do the same thing for the number of columns, that is how many columns we have in the horizontal direction. So here we'll take the width of our canvas and divide it by the horizontal size of each cell. And then lastly, we can create the cells. Now for every row in range, self.number of rows. And for column in range, self.and cols. Well, we'll append to our cells list. So self.cells append. What are we going to append? A new cell with row and column. And that's really it for our grid at the moment. Now, I haven't included the people in there yet, but, well, we'll do that right now. So self dot, and now how are we going to be storing these people? We'll just create a function that I'll call store people. So for now, self.people, well, no, we'll just say self.store people. And this is a function that we now have to create, okay? So we are going to take our people and we'll use the function store people, and this will then take care of the rest. This will assign the people that we are passing into the class to the cells that are not defined when we first initialize the grid. So after the initialization function, we now have to write a new function, a new method for storing people. Store people. Take self and then people. Okay? So how does that work? We'll simply say for p and people. So each person is now assigned to the cell depending on where it's located. So we now have to translate people's x and y coordinates into rows and columns of where they have to go within the grid. So here we'll say the row. Well, the row, what is it equal to? It's equal, well, the row, that's, how high or low it is on the canvas. So that's, the y coordinate. And now we'll simply divide that by the vertical size of each cell. And this will then tell us how many rows up or down it is on the canvas. And well, since row cannot be a floating point number, it has to be an integer. So we'll use the integer function to make sure it is actually an integer. So we'll divide person P's y coordinate by the vertical size of the grid cells. And then we'll do the same for the column with the x coordinate. So self.h size here. And given the row and the column, we can compute the index position of the cell in question within the cell's object of the grid. So here, let's just call this index. This is equal to row times self.mcols plus column. That's really just a nice little equation that translates the row and column into the index as they are stored in this list here. Okay, so let's say self.cells index dot people dot append p. That's a lengthy line, but essentially we're just going to go into the cells object of the grid class. Then we'll go into the people object within the cell itself, because we are going into a cell that is the cell at index location index, and then we're going to be appending to these people the current person P, and that's really it. Okay, so let's see whether that works. So down here, I'll now create the grid. Grid is equal to grid, and here I'll now pass our people's list into this, and that's all we need. And I'll throw everything else here inside a comment because we don't need the game window or anything, the animation window. I'll just run this. We don't get an error, so I think up until this point this looks good. But to be sure, let's print our grid. It says it's a grid object at that particular memory location. Of course, that doesn't matter. So let's print the first of the cells. It now says this is a cell object. This seems to be working. So let's print the people. That's an empty list, so the top left corner is empty. So let's loop through a bunch of cells. So for I in range 100, print the person in these cells, and voila, there we go. So yeah, a lot of cells are empty, nobody's in there, but then some cells have people stored in them. So that is working. Nice. Let's delete this. Of course, it's good to know that the grid is working, but I think we'll conclude this video by trying to visualize our grid as well. Okay, so I'll go back up here into our grid class. Now I'll implement another show function here, which will help us visualize our grid. So I'll specify just one optional parameter here, which is the width of how thick the lines are to be drawn here. Okay, so for C in self.cells, we're looping through all the cells in our grid. We are first inferring the X and Y locations. This is because the cells have only rows and columns stored in them, but not the X and Y locations. So we'll have to convert this back, and we can do that by multiplying the column with the horizontal size. So for each cell, we are essentially computing the top left corner here of the cell, okay? And then with Y, we'll take the row and we'll multiply that with the vertical size. Now we define a little rectangle using pygame.rect. And here we now use our X and Y locations to specify the location, and then we'll have to set the width and the height, which is really nothing but self.h size and self.v size. Once we've done that, we can draw this rectangle using pygame.draw.rect. Now we have to specify the screen, which is where we are drawing this. Then we'll have to go into our color definitions and select, I think I'm going to be using light gray here because, well, the background is dark gray. And now, what is it that we are drawing? We are drawing the rectangle object, and then we'll set width equal to width. And I think this should be it. So let's go down here. We have our pygame loop. Let's bring that back in. Let's create our grid once more. Good thing I deleted that. And okay, let's remove this. So we have our grid, and now right after the background color, I'm going to use grid.show. And there we go. You can now see the animation let's remove some of the points here. Let's not make this 1,000 but 100. And now you can really see our grid here, and of course, currently, maybe the size of the cells is a little bit too small, so we might increase this. And yeah, this is also a good check on whether our code is working in the way it's supposed to. So let's change the horizontal and vertical size of our cells, okay? So let's exit out of this. Yeah, let's go in here and set h size equal to 100. And yeah, there we go. So now it's no longer a rectangle because remember the vertical size of the cells is still initialized to 20. And if we have a different height in comparison to the width for each cell, then we have rectangles instead of squares. And yeah, so this is working. Let's set the other one as well. V size is equal to, say, 200. Let's both make that 200. And now we have a, we have a grid with pretty large cells. This is working just as it is supposed to. And I think this is now enough for this video. In the next video, we'll now wrap everything up in a new class that I'll simply call Pandemic. And this Pandemic class will then, control all of the features of our animation. And we'll then only have to deal with this one class in the future. Of course, if we are adding new features, we'll also have to deal with the persons class again. But when we are running things, we'll only make use of this new Pandemic class, which is what we'll do in the next part of the series. See you then.